G'day, welcome to our final topic in our inorganic section of our chemistry course, looking at nitrogen and sulfur, where we're going to start today looking specifically at nitrogen. Our lesson objective is to understand the properties and uses of nitrogen and ammonia. Nitrogen is a very important element. It is found as the majority of our atmosphere, about 78% of the atmosphere and the air we breathe is unreactive nitrogen gas. It has an atomic number of 7, which means it has 7 protons, and a neutral nitrogen atom is going to have 7 electrons. So we find it existing as a diatomic molecule, which we can rationalize based on the electronic configuration that it will have. So if we have our nitrogen atom with its 7 electrons, we're going to have 1 s2, 2 s2, 2 p3. 2 plus 2 plus 3 is 7 electrons. So that means we're going to have 5 electrons in our valence-most shell. That means if we draw a simple Lewis dot structure of nitrogen gas, we'll see that it can form 3 bonds to get that noble gas stable electron configuration. So with another nitrogen atom, we're going to have covalent bond there, covalent bond there, covalent bond there, which will give it a very strong and a very stable triple bond, 1 sigma 2 pi. A very stable triple bond that has a high energy. It is around 950 kilojoules per mole of energy in that triple bond. So as you can imagine, it's going to take sort of extreme conditions, harsh conditions in order to break this bond and make it react. But we do look at a few reactions of nitrogen. We're going to look at the formation of the oxides of nitrogen, which we see occurring both naturally and also through human activity. Let's look at how this oxide forms first of all. We have our nitrogen gas. Our diatomic nitrogen gas can react with our diatomic oxygen gas to form a nitrogen oxide here. We can then have further oxidation to nitrogen dioxide, which has the nitrogen in this +4 oxidation state, as opposed to this +2 oxidation state here. So this can undergo further oxidation where it reacts with another molar equivalent of oxygen gas to form the nitrogen dioxide, nitrogen 4 again, because that's going to be a +4 oxidation state for that nitrogen. But like we just said, it's a very strong, it's a very stable bond. This only occurs under extreme conditions. We find this occurring naturally with lightning. If we have lightning, that's a huge amount of energy that's occurring up in our atmosphere. That can provide the activation energy naturally for these oxides of nitrogen to form. And then the other main place that we see it is due to human activities. We see it in the internal combustion engine, for example, in our vehicles that are so populous on the road. So in our internal combustion engines, we got high pressures, we got high temperatures, harsh reaction conditions. We can have the nitrogen and the oxygen in the atmosphere that's just going to be in the internal combustion engine, reacting to form these oxides as a result of this. So it can also occur in the internal combustion engine where fuel is compressed and ignited, high temperature and pressure, sufficient to form oxides that are then released into the atmosphere. But these oxides, especially at the higher concentrations that we are releasing them into the atmosphere, they're acting as pollutants and is having lots of knock-on and snowballing effects in terms of environmental and infrastructural damage that we'll see momentarily. So to counteract this, most modern cars will have things called catalytic converters that remove the oxides catalytically using a catalyst, converts them back into harmless nitrogen gas and other byproducts that won't damage the environment in the same way that these oxides will. So these oxides of nitrogen dissolve in rain, and as part of the natural nitrogen cycle, they do fall back to Earth in rain in the form of HNO3, nitric acid. These provide necessary nitrate ions for plants. Nitrogen as an element is incredibly important for plant growth, but as we'll see and as we've discussed from the unreactivity of it, it can be difficult for N2 to be the source of nitrogen. It often has to be converted into something that is more reactive so that it can be consumed by the plants. And this nitrogen cycle, converting to this nitric acid, is one way that the Earth has established itself to do that, where the NO2 gas reacts with the water and oxygen to do this, and this can provide the nitrogen necessary for plants. But like I was saying just before, the increased concentration and frequency with which we're pumping this NO2, these oxides and nitrogen into the atmosphere is causing lots of detrimental effects to the environment, such as photochemical smog and catalyzing sulfur dioxide gas to form acid rain, sulfuric acid. This is something we'll look at a lot more detail in our sulfur lesson in the next lesson, but just be aware that it catalyzes sulfur dioxide to form acid rain. Let's talk now about ammonia, a very important nitrogen-containing compound. It can be synthesized from nitrogen and hydrogen via something called the Haber process that looks like this. Nitrogen gas plus hydrogen gas is in equilibrium with ammonia gas, 1 to 3 to 2 being the mole ratio to make that nice and balanced. Incredibly important reaction. In fact, it won the fella Haber, Fritz Haber, who was one of the fellows who discovered it, won him a Nobel Prize in chemistry. The reason it's so important is because it can create the fertilizers that support the majority or a large proportion of the Earth's population by allowing the crops to grow, whereas naturally these crops wouldn't be able to grow because there would be insufficient nitrogen for the rate with which we're removing the plants for them to regrow and thus keep feeding us. So it's a very important reaction. It's the main process of producing ammonia that is vital supporting a lot of the world's population. Discovered by these fellas called Fritz Haber and Carl Bosch. Like I said, Fritz Haber won the Nobel Prize in chemistry for this process in 1918, but he also spent years weaponizing poisonous gases for chemical warfare in World War I. So quite interesting. On one hand, he's developed a process that has saved and fed millions and millions of people, but he's also developed a process that has, caused many deaths, many painful deaths through chemical warfare. Interesting fellow, worth having a read up about him. But let's do a question to move on from that. Can you draw a 3D ammonia molecule, name its shape, and show its bond angles? Pause, do those 3 things, and check it now. Ammonia, NH3, is going to have lone pair of electrons. It's got one bond with a hydrogen, another bond with a hydrogen, another bond in a hydrogen. In a 3-dimensional space, this is going to have our trigonal pyramidal. Remember that our lone pairs of electrons cause repulsion. In fact, they cause more repulsion than our bonding pairs, and they are also responsible for pushing these down into that trigonal pyramidal, sort of based off of our tetrahedral, just without that extra 4th bond going up. Now, the bond angles that we would expect to see is 107 degrees. Smaller than that of a tetrahedral, but larger than that of a V-shaped. Let's look at this Haber process in a bit more depth. So, it uses nitrogen from the air, like we just said before. 78% of our atmosphere is unreactive nitrogen, so we've got plenty of nitrogen that we can extract from the atmosphere in order to use it to make this ammonia. And the hydrogen from mainly natural gas. It reacts these in a 1 to 3 ratio due to the mole ratio of the equation. And it has these conditions. We have a high temperature, 450 degrees Celsius, high pressure, 200 atmosphere, and we have an ion catalyst. Liquid ammonia is then collected when the gas is cooled, so that's drained off. Unreacted gases are recycled, and we can make sure that we use as much of the reactants as possible. Let's consider what we know about equilibrium and reaction rates to consider the effects of temperature, pressure, and catalyst on this instance. Because a lot of the time you need to have a consideration between how quickly you want the reaction to occur, especially on an industrial scale like this ammonia, manufacture of ammonia would be, versus how much yield you can get. So ideally you want to get as much yield as you can as quickly as possible, but depending on the reaction conditions and what we know about things like Le Chatelier's principle, that is not always possible, so there has to be considerations. For example, our formation of ammonia, this Haber process, is an exothermic reaction. So if we were talking strictly and purely from an equilibrium point of view, we would want a low temperature to increase the yield as much as we can because we want to favor that forward reaction. However, we also know that by decreasing the temperature, we're going to slow the reaction rate down, and that's going to mean it takes longer to form. So I mean, there's not much point if we're going to form 100% ammonia, but if it's going to take weeks to do it, then that's not particularly useful for an industrial standpoint. So we use a high temperature, or the people who manufacture it, I should say, use a high temperature, even though that's going to push the equilibrium to favor the endothermic, so the backward reaction in this case. It's going to increase the rate of reaction, so we're going to produce ammonia faster, so it's that sort of trade-off that you have to consider between the two factors. Let's look at the pressure. High pressure, well, we've got 4 gas molecules on the left-hand side, 2 gas molecules on the right-hand side. The pressure here is going to push the equilibrium to the right-hand side to favor the yield of the ammonia, also going to increase the reaction rate, higher frequency of collisions. So you can see we've got a high pressure that is favoring the forward reaction, so this can sort of work in tandem with the high temperature that is sort of favoring the backward reaction, but also increasing the rate of reaction. So it's all about these considerations, like I say. Then we have our catalyst. Our catalyst increases the rate of reaction, has no effect on equilibrium. Equilibrium is just reached quicker. So we can increase the rate with all 3 of these things, increase the yield with our high pressure, and these trade-offs gives us a good amount of ammonia for that economic benefit. I mean, again, if you're talking from an industrial standpoint, you want that cost-benefit ratio to weigh out. Okay, let's look at the ammonium ion now. Ammonium can form a coordinate dative bond with a hydrogen from an acid. So if we've got a H plus acting, that is from an acid, acids are acting as our Bronsted-Lowry acids, they're proton donors. We can form an ammonium ion, which means if it's reacting with an acid, the ammonium will be acting as a base. It's also acting as a base because it is accepting a proton, and that's a Bronsted-Lowry definition of a base. So we have a lone pair of electrons here. We have a H plus that has an empty orbital. We can form a dative bond with the H plus to form the ammonium ion. We can put that in brackets, positive outside the brackets to show that positive is spread out over the whole molecule. So now we've got a cation. We've got a positively charged polyatomic cation that can form ionic salts with anions. Yep, so they can form an ionic salt with an anion. So let's look at this application of fertilizers. So the reason I said before why ammonia is so important is because it can be used in fertilizers that can replenish the nitrogen much quicker in the soil for the plants to use and grow than would occur naturally through, I guess, the natural nitrogen cycle. So very important for plant growth, but like we've said, it's very unreactive, triple bonds, very strong. The plants can't just get that nitrogen from the atmosphere because it is too unreactive. So we saw it does that naturally by getting nitric acid from the rain after we form the oxides of nitrogen. And that's one way that it can get it, but we can do this artificially by making these ammonium salts. For example, ammonium nitrate, ammonium chloride, ammonium sulfate. These are all water soluble, so we're going to get the displacement of the ions from the salt. So if we put these with water, we get the ammonium ions. The ammonium ion is now much easier for the plant to take it up through the root and get this delicious source of nitrogen that it needs to grow. So we've got these things called NPK compound fertilizers. If you pause, probably work out what the NPK is. It's referring to nitrogen, phosphorus, and potassium. So these are the elements that are most commonly lost from extensive soil use. If you think agriculture on a large scale, constantly planting, constantly digging up, constantly planting again, we're constantly changing the nutrients in the soil, and because it's not given ample time to re-establish the levels that it needs naturally, we can artificially put this in through these fertilizers. As plants are being removed, they aren't rotting and replacing these elements naturally. Okay, so that's one application of our ammonium ion and our ammonia. We can also do a qualitative analysis. We talked about qualitative analysis in the previous lesson. These are experimental chemical tests we can do to identify unknown compounds. So we can do a qualitative analysis for an ammonium ion, and if we see a certain result, we can infer that our unknown has an ammonium ion. And what we do is we heat up the unknown, and if we see ammonia gas being produced, we can infer that that's come from ammonium. Ammonia gas is a base. We've talked about ammonia acting as a base up here. If we got it in the gaseous form, we can then just do a identifier of a base, turning damp red litmus paper blue. Therefore, it will be showing it's a base. For example, thermal decomposition of ammonium chloride will form that ammonia gas that's going to turn the red litmus paper blue. Let's finish up today looking at some uses of ammonia and ammonium compounds. So we've just been talking pretty in depth about fertilizers, the acid-base reaction of ammonia to make ammonium salts that are water soluble. Put them in fertilizers, bit of water, the plants can take them up and extract that nitrogen that they need to grow and be delicious for animals and also just to look pretty. Question, here's what I want you to pause and have a go at. Write an equation showing the formation of ammonium nitrate from ammonia and nitric acid. So we've got the product, we've got our reactants, this would be our fertilizer. Pause, write an equation. It should look something like this. Ammonia, aqueous, plus the nitric acid goes to our ammonium nitrate, our water-soluble fertilizer that we can ship off to anyone who needs it. So what these are done, they are dehydrated to get all the water out. The water's evaporated, they're melted, and they're solidified into pellets that can then be spread easily, from a tractor if you're doing that on a industrial scale. And then with the water, they're gonna dissolve and get into those plants. However, there is a problem with the environmental aspects of this increase in fertilizer and these increase in these nitrogen compounds. The water solubility of ammonium salts can be leached out of the soil by rain into groundwater that makes its way into major water sources. So like we looked at when we were talking about the increase of the oxides of nitrogen in the atmosphere, if we have a increase of these ammonia compounds, they're going to throw out the this equilibrium that's been established in these ecosystems over a very, very long time. The Earth has developed itself in a very precarious balance, if you will, and a lot of the human interactions, a lot of the human activities that we're doing is throwing this balance out of whack, and we're seeing lots of negative environmental effects as a result of this. So why would this be bad? If it leaches out of the soil into the groundwater that makes its way into major water sources, well, we get our drinking water from these water sources. There could be potential health risks associated with this. Now, it can also enrich the growth of algae and marine plants, which is a process called eutrophication. So we've said that ammonia is really good for plant growth, but this could be bad if we have an increase, and again, it's throwing this equilibrium that's been established in an ecosystem out of whack. For example, algae can block out light. Algae can develop all on the surface of a river, and that can block the light from getting through into the river. And that means that all those important organisms that require on that UV light beneath the surface of the water are now not getting it and are dying because of it. Can also cause the bacteria that feed on them to multiply and use up the dissolved oxygen in the water. This leaves insufficient amounts for larger marine life that will consequently die because they're not getting that oxygen that they need. This will have chain reactions on the entire food chain. Similarly, overgrowing of marine plants will be negative for the ecosystem as well. Again, just throwing that established equilibrium out of whack is going to have snowballing effects that go on. Some other uses of ammonia and ammonium compounds: cleaning products, fibers, explosives, synthesis of other chemicals, many, many things. And with that, we've looked at our first lesson on nitrogen. What have we done? We've explained the lack of reactivity of nitrogen, described and explained the basicity of ammonia, the structure of ammonium ions and its formation by an acid-base reaction, and the displacement of ammonia from its salts. Stated the industrial importance of ammonia and nitrogen compounds derived from ammonia. State and explain the environmental consequences of the uncontrolled use of nitrate fertilizers. State and explain the natural and man-made occurrences of oxides of nitrogen and their catalytic removal from the exhaust gases of internal combustion engines. And we've explained why atmospheric oxides of nitrogen are pollutants, including their catalytic role in the oxidation of atmospheric sulfur dioxide. We'll look at this in a bit more detail in the next lesson that's looking at sulfur. Tasks for this lesson. Can you pause, work through these, and you will have consolidated your understandings. Thank you very much. See you on our next lesson when we conclude this unit by looking in depth at sulfur. Have a good one.